3. Pressure and Fluid Statics. Welcome to Chapter 3. This is where fluid mechanics starts to feel real. We're going to talk about pressure and fluid statics, two of the most practical topics in engineering. Why do dams get thicker at the bottom? Why do scuba divers feel more pressure as they go deeper? It all comes back to pressure. We'll break down how pressure works in fluids, how it changes with depth, and how it applies to real-world designs. Simple examples, useful equations, and practical applications. That's what this chapter is all about. Get ready to connect theory with the things you see around you.
Let's clear up the idea of pressure, because it's more than just a number. It's a basic principle that explains how fluids push on surfaces. Pressure is simply force divided by area, measured in pascals. But here's where engineers need precision. Absolute pressure starts from zero, like space, with no air at all. Gauge pressure starts from the atmosphere around us, so most pressure gauges you see ignore atmospheric pressure. Vacuum pressure, that's just pressure lower than the air we breathe. Think of a vacuum pump sucking air out. Remember, gauge and vacuum pressure are just tools to measure how much more or less pressure we have compared to the atmosphere. Two simple formulas tie it all together. Absolute minus atmospheric gives you gauge pressure, and atmospheric minus absolute gives you vacuum pressure. Simple, logical, and directly useful in real applications.
2. Make pressure variation easy to understand. Let's talk about why pressure changes when you go deeper in a fluid. It's simple. Fluids have weights, and that weight presses down on everything underneath. The deeper you go, the more fluid is above you, so the pressure increases. The equation for this is called the hydrostatic pressure formula. P equals P naught plus rho GH. Each part of this formula has a clear purpose. P naught is the pressure at the surface, like atmospheric pressure. Rho is the density of the fluid. Heavier fluids push more. G is gravity. It's why things have weight. And H is how deep you go. Just like diving in a swimming pool, the deeper you go, the more you feel the pressure. This equation keeps things straightforward. More depth means more pressure, always. 3. Simplify pressure measurement tools. Let's make pressure measurement simple. We have different tools because not all pressure is the same. A barometer is for atmospheric pressure. It uses a mercury column to show how much the air pushes down. That's why we call sea level pressure about 760 millimeters of Hg. Then we have manometers. They use U-shaped tubes to compare pressures between 2 points, like a basic balance scale for pressure. The height difference tells you the pressure difference. Other tools? Board-on tubes are what you see on mechanical gauges, simple and tough. Pressure transducers are for converting pressure into electronic signals, perfect for machines. And when pressure changes quickly, like in engines, we use piezoelectric transducers because they respond fast. Each tool has its purpose, and knowing when to use which makes you a smart engineer. 4. Make fluid statics easy to remember. Here's how to keep fluid statics simple. When fluids are at rest, they don't move sideways, meaning no shear stress. They only push straight out, which we call normal stress or just pressure. That's why you can float calmly in water. The key rule here is Pascal's Law. It says that any pressure you apply to a trapped fluid spreads equally in all directions. Like pressing a balloon. Push in one spot, the whole surface pushes back equally. This principle powers hydraulic systems like car brakes and hydraulic lifts. One simple law explains so many everyday technologies. Remember it. 5. Simplify hydrostatic forces on submerged planes. Here's how to think about hydrostatic forces without getting lost in formulas. When a surface is underwater, the fluid pushes on it with a force called hydrostatic force. It's simple. Just take the pressure at the middle of the shape, the centroid, multiply it by the area, and you get the total force. This force always pushes straight, perpendicular to the surface, never sideways. But where exactly does this force push from? That's called the line of action, and it's a little below the center because deeper parts feel more pressure. For rectangles, a shortcut is the force acts at 2/3 the depth from the surface. No need to memorize complex math. Just focus on these simple ideas and you'll master it. Curved surfaces look complicated, but you can simplify them by breaking forces into two directions, horizontal and vertical. The horizontal force is easy. Just imagine flattening the curve into a vertical wall, and the pressure on that wall gives you the horizontal force. For the vertical force, don't overthink it. Just count the weight of all the liquid sitting above the curve. Simple rule, Fv equals RhGV, meaning weight is volume times gravity. And here's a shortcut for circles. On circular surfaces, all these forces combine and go through the center of the circle. No complicated math, just geometry and common sense. 7. Make buoyancy and stability effortless to understand. Let's simplify buoyancy and stability into something you'll never forget. Archimedes' principle says if an object pushes fluid out of the way, the fluid pushes back with the same force. That's buoyancy. The denser you are compared to the fluid, the more likely you are to sink. Less dense? You float. Easy rule. Stability is just about how wobbly you are. The metacenter, M, tells you this. If M is higher than your center of gravity, G, you stay upright, stable. If M is lower than G, you tip over, unstable. Simple density checks tell you float or sink, and metacenter checks tell you stable or unstable. Keep it that clear. 8. Make rigid body fluid motion clear and simple. Let's simplify rigid body motion. Sometimes fluids move like a solid block, without waves or internal swirling. That's what we call rigid body motion. If you accelerate a tank forward, the water tilts. Why? Because the fluid reacts like a slope, forming an angle theta that depends on acceleration over gravity. Easy rule. More acceleration, bigger tilt. Now imagine spinning water in a glass. What shape does the surface make? It forms a nice, smooth parabola. The faster it spins, the deeper the sides get, and the higher the edges rise. The equation helps predict this curve, but the concept is simple. Acceleration tilts it, rotation curves it. Focus on those two effects, and you'll always understand the big picture. 9. Make your fluid static summary clear and memorable. Let's wrap it up by keeping only what matters. Pressure goes up when you go deeper. Simple rule. We use barometers and manometers to measure it depending on what we need, absolute or difference. Hydrostatic forces, they depend on how deep you are and how big the area is. Buoyancy, always linked to the volume of fluid you push away. Floating is not just about floating, it's about staying stable. Watch the metacenter. And finally, when fluids move like a solid body, they tilt or curve depending on acceleration and rotation. No extra words, just the essentials to remember the big picture.